Okay, so we do have some application problems for square roots. So many applications translate to radical equations. For example, temperature. So at a temperature of T degrees Fahrenheit, sound travels s feet per second, where s is going to be equal to 21.9 times the square root of 5t plus 2,457. So basically what we see is that we're seeing sound kind of travels like this. So really what it is like your speed of sound, it's getting faster, faster, but it like here it gets faster quicker, and then it gets faster slower here. Actually, let me write that equation. So we have it here for our next couple questions. So S equals 21.9 times the square root of 5t plus 2,457. So this question says, during an orchestra practice, the temperature of a room was 47 degrees. How fast was the sound of the orchestra traveling through the room? So we just want to figure out what S is. So 21.9 times the square root of 5, and T is my temperature, so that is where 47 goes. So 5 times 47 plus 2,457. That is going to be 2,827. So the square root of that, or raise my decimals of it if I can down, that is 53.1695401, and it will just keep on going. So if I take that and I multiply by 21.9, I'm going to get a speed of 1,164, and we're going to round this, so 64 point, this is rounded two places, 41. And remember, this is, actually, what is this in? I forgot. Speed is in feet per second. So how fast the sound traveling through this, the sound of this orchestra traveling through the room is 1,164.41 feet per second. Okay. All right, so we're asked two questions here. So we're still using that same formula. So during an opera performance, the temperature of a room is 68 degrees. How fast is the sound of the orchestra traveling through the room? The second question might take a little bit of thinking about. If the sound is traveling at 1,120 feet per second, what is the temperature of the air? So take a moment and see if you can figure both of those out. So your first question is telling you T. It's telling you the temperature in the room. And it's asking me to find sound. So the sound is just going to be 21.9 times 5 times the T, which is 68, plus 2,457. So I'm going to put that all in my calculator and not do it in bits this time. Okay. And if I do that, let me just do this one little bit here. So the square root, you're going to do a square root of, and here comes 2,797. So 21.9 times the square root of 2,797 is approximately, if we round to 2 decimal places like we did last time, 1,158.22 feet per second. So the second part is telling us the sound how fast the sound is traveling already and asked for the temperature. So it's telling us S. So if we go back to our equation, what we actually have is 1,120 is equal to 21.9 times the square root of 5t plus 2,457. So we're solving a radical. So all I have to do is just get the radical by itself. So I'm going to divide both sides by the 21.9. So 1120 divided by 21.9. I think we'll have to leave that as is because it's not going to get any nicer. So we'll leave it as that fraction because otherwise we get kind of a big messy decimal. But we know that what's going to happen here, the 21.9s are going to disappear, and then I've isolated the radical. So if I just square the radical and I square the other side, we're going to have 1120 divided by 21.9 squared is going to be equal to 5t plus 2,457. So I just need to isolate t. So I'm going to end up with, we'll write 5t over here first. So 5t is going to be equal to 1,120 divided by 21.9, all of that squared, minus 2,457. Then t itself would just be 1,120 divided by 21.9 squared minus 2,457. And now all this is going to be divided by 5. So if I stick that on my calculator as one, just lump sum. And I'm doing it this way because it's going to make sure that my calculation is as close as I can get it before I approximate. And what I'm getting is the temperature of this room is going to be approximately 31.69. So we'll say approximately 32 degrees. So we're at freezing. We're at a freeze point in this room, and this is how fast the sound is going.